Hello everyone, welcome to this lecture from Vizuara AI Labs. Today we are going to look at a hands-on neural network project. At the end of this lecture, you would have constructed a neural network model on a very practically oriented problem. The problem which we are going to be looking at today is called as the California Housing Price Predictor. It's a regression problem. So I'll first explain the data set to you, then I'll take you through the neural network architecture, and then we'll do the training and then we'll do the testing. If you want to understand every single detail about the optimizers, let's say the forward pass, the backward pass, we have another series on our YouTube channel called the Neural Networks from Scratch. So I would highly encourage all of you to go through that series to understand the concepts. This lecture will be purely a practical lecture, and I would not dive into the theory too much. If you are planning to prepare for an interview and if you want to do some hands on projects which you can add to your resume, this lecture will be very useful to you. So, let's get started with today's lecture. So, as I mentioned, the topic which we'll be looking at today is called as the California Housing Price Predictor. Before we start any project, it's very important to really understand the data set and what we are essentially trying to predict. I see many ML engineers make the mistake of directly importing packages, directly running the model. But first ask yourself the question, what does the data set look like? Have I understood the data set? What's the problem I'm trying to solve? Is it a regression problem or a classification problem? And then you can move ahead. So I'm going to show you the dataset now. The dataset is provided by default from this library called Keras. So keras.datasets is the main function, and then you can load various datasets. Here you can see that in this dataset there are basically 8 input features related to houses. The medium income in a block group, the median house age in a block group, etc. So first you might think, what's a block group? That's also defined over here. A block group is the smallest geographical unit for which the US Census Bureau publishes sample data, and it can have a population of 600 to 3000 people. So we are looking at block groups here and not really individual houses. So for the first two, for every house, we are going to have these input features. We are going to have the medium income in block group. We are going to have the median house age. Then we are going to have average number of rooms, but remember they are per household. They are not per block. Then we have average number of bedrooms. We have the block group population. We have average number of household members, which is how many number of people are there in an household. And then we have the location of the block, latitude and longitude. So then you must be thinking, okay, if these are the input features, what's the output which I'm trying to predict? The output which you're trying to predict is the value of the house. So the main goal is that if you're given all these features related to a house, what is the value of the house in dollars? Now ask yourself the question that does this make sense? Would all of these features actually contribute to the value? So let's look at it individually. Medium income. So if the income of the people is higher, they would generally take expensive houses. So it definitely matters. House age. House age definitely matters because the older the house is, its price will be proportionally higher. The price, of course, depends on the number of rooms and the number of bedrooms. Higher number of rooms and bedrooms would increase the price of the house. It depends on the population of the block as well and the average number of household members. Finally, as we know, in any location you go in the world, there are some specific areas where the housing prices are generally very high. And that's why the latitude and longitude of the block group also matter a lot. So this makes sense to you, but you still want to know the units, like when we say median income, income in what? Is it in dollars? Is it tens of thousands of dollars? So that you can get a sense of the range of the data. So let me try to show you what each different variable means and the range for each variable. Sometimes you can do this in Google Colab itself, and I'll show you how to do that. But for this data set, it's a pretty standard data set, so all this information is available online. So let's look at the median income first. The median income means that it's the median income for households within a block of houses, as we saw, but it is measured in tens of thousands of US dollars. So if this value is 15 in the data set, it means its actual value is 15 into $10,000, which is 150,000 US dollars, which makes sense. Then let's look at total rooms and total bedrooms. They lie between 2 and let's say 40,000. Now remember, total rooms and total bedrooms within a block, and that's why the values can be so high. Then population is number of people residing within a block, and its minimum value is 3 and its maximum value can go as high as 36,000. The median age of a block. So for this data set, this lies anywhere between 1 and 52. And then latitude and longitude, it just values ranging from minus 180 degrees to plus 180 degrees. And for the data set which we have, the minimum value is minus 124.3 and the maximum value seems to be minus 11443. Let's look at the data type also. That's also another important uh, value. So all of these data types are floats, which is good. Ideally, if they are integers, we would want to convert them into floats for all the operations, for all the mathematical operations which we do later. Okay, so this is the data set, and we typically understand what each variable means, what's its data type, and what's the range of values, what's the unit of that variable, and we also intuitively understand why these features can contribute to the price of a house. Great. Now let's actually load the data set and try to see in code. So as I mentioned, there are 8 input features: the median house age, average number of rooms, average number of bedrooms, block group population, average number of household members, block group latitude, and block group longitude. The target variable is a scalar, which is the median house value for that particular block or district in dollars. Now, let's actually start with the code. Initially, we'll be loading packages. So, we'll be loading TensorFlow as the main machine learning library, and within TensorFlow, we'll utilize the Keras API. And then we'll be loading 3 common packages: NumPy for scientific computing, Matplotlib for plotting graphs, and Pandas for converting datasets into tabular format. These three are pretty common libraries which you will encounter in many Python codes. So let me run this code block right now, and as we'll see, it takes some time to load these packages, but once they are loaded, then you can use all the commands which come built in through these packages. So you'll see a tick sign here when that particular code cell is executed, which means that you can go to the next code cell. Now what we'll be doing is that we'll actually be fetching the data set. So actually, this California housing data set is obtained from the sklearn library and not Keras. So similar to Keras, sklearn also has the data sets, and we can fetch the California housing. Even Keras has this, so you can even do keras.california housing. But we will use the sklearn to fetch this data set. So that's the first thing which we fetch. The second thing which we fetch is something called train test split. This will automatically split our data into training data and testing data. And finally, we'll import a function called standard scaler. I'll show you what this means, but it's basically for standardizing the data. We will subtract the mean and divide by the standard deviation. You can always hover over to that particular function, and then in Google Colab you can see the meaning of that function. Like you can see the meaning shows up over here, and you can understand what it represents. Great. So this is the command housing equal to fetch underscore California underscore housing, which will fetch the housing data set for you. And then what we'll be doing is that first we'll be dividing the data set into training and testing. So I believe the data set consists of 20,640 samples, and it already comes with training and testing. So you don't have to mention the train test split ratio. Usually you will have to mention this ratio in other data sets. So right now we'll just do train test split of housing data, and we mention housing dot target, which is the target y values, and we mention this random state. so that it's replicable every single time. What we'll do is that we'll further split the training data into validation data. So we'll take a small chunk of the training data and use it as the validation data set. So this is the first piece of code which I'm going to run right now. So you can see the green tick has appeared, which means this code has successfully run. And now let us try to investigate what we have loaded here. So this X train full is our training data set. Let's first see the length of this. So I run this and I see that the length is 15480. And then so the remaining will be around I can even print the length of the X test. So the remaining would be X test, which is 5160. So I'm typically using a ratio of, I think, exactly 1 is to 3. So one third samples are used for testing and two third are used for training. But we will not stop here. We'll actually also print the validation and see how much it is. Now we'll take this 15480 and we'll split some of it into validation. So let's see what the validation uh, length is. So the validation length is 3870, which means that out of this 15480, 3870 are used for validation and only the remaining will be my final training set. So let me print this. This is given by X train, and I'll show you what the value of this is. So the length of this is 11610. So finally we'll be using 11,610 training samples, 3870 validation samples, and 5,160 testing samples. Now let us actually see how this data, how the training data looks like in a tabular format. So I'm going to take the X train full, which is 15480, or I can even maybe take the X train, I guess. So let me just take the X train, the final training data, and let me print it in tabular format. So for that, we are going to use the pandas package which we have loaded. So we did import pandas as PD. So when we do pd.data frame, what it will do is that it will take the X train and it will convert it into a tabular format. You can try printing out just the X train, but you will see that it does not get printed in a easy to understand manner. So if you just print the X train, it will look something like this, not formatted very well, right? That's why we have to use pandas. So I'll convert the X train into a data frame and I'll print it, and I'll name the columns as the feature names so that I can see the values of every feature. So let me run this right now. Okay, so if this information of the data set was not available to us, like I showed you on this Google site, we can just investigate in Colab itself. So right now you can take a look at the features: medium income, house age, etc. 8 features, and I printed it out for the 8 houses, and you can see the values. So the median income is 3, 5, 3, 7, etc. The house age is 15, 5, 29, etc. The latitude values are around 37, longitude values are negative around 110, and the population is generally in the range of thousands. So this is how the data set actually looks like. And here I'm printing the length of X test, but we have already seen this before. So let me delete this code cell. Okay, so I'm deleting this code cell right now. Um, Now, do you see some sort of a problem with this data set? Uh, Take a look at the maximum and the minimum values of different features, right? So, for example, the median income lies between 1 and 10. It seems like the house age is of a higher magnitude. The population is of a further higher magnitude. It's in the thousands. The longitude sometimes takes negative values. The problem with neural networks is that if you have features on different scales like these, the training becomes very hard. For example, the features with higher values, like in this case population, may sometimes dominate the features with lower values, such as the average number of bedrooms. And so the weights associated with the features with lower values tend to be sometimes very small, and then those weights won't update. It leads to many problems in the neural network training. So generally, when you see a data set like this, which has the feature values on different scales, the best option is to standardize them, which means that you need to convert them into some sort of a normal distribution like this. You need to make sure that, let's say, the population has a range of values. You need to standardize those values, which means that you need to make sure that their mean is 1, and you need to make sure that the standard deviation is, sorry, mean is 0 and their standard deviation is 1, so that the all the feature values roughly lie between -1 and 1 roughly. There might be some features -2, -3, but those will be very small, because in a normal distribution, standard normal distribution, those are very small. So generally we would want all of our features to be lying between -1 and 1. And the way to do that is, we'll take the, let's say, the population values are a giant array. We'll take that array, we'll find the mean of that array, and we'll find the standard deviation. From each value, we'll subtract the mean and divide by the standard deviation. What this will do is that it will bring the entire uh, array of the population into a normal distribution like this, which will make sure that the mean is 1, a mean is 0, and the standard deviation is 1. And the function which helps us do that is called as standard scalar. So the standard scalar function, here you can see I have loaded the definition. You can just mark that particular function, and then the definition shows up in Python. So you can see what the standard scalar function does. It standardizes features by removing the mean and scaling to unit variance. So we'll subtract the mean and then we'll scale with the unit variance. And we'll do this for all the training data, the validation data, and the testing data. So we'll do this for all the data, the training, validation, and testing. The way to do this is that you define scalar is equal to standard scalar. And remember, we have already imported standard scalar from scalar or scikit-learn. And then we'll do scalar.fit.transform or scalar.fit underscore transform of the training data. And then we'll do scalar.transform of the validation data. And then we'll do scalar.transform of the testing data. So this is how we can standardize the training, validation, and the testing data, so that the neural network training becomes much easier. If you are watching this video and if you run this code, I strongly encourage you to remove this and see the training for yourself. You'll see that the training is much slower actually, and then you will understand the importance of this standardizing even more. So we already saw the length of the final X train, it's 11,610, and the validation is 3870. So let's move further down. So we'll be setting this np.random seed and tf.random seed. And the reason we do this is because when Keras initializes the neural network, it's the weights and biases are initialized to random values. So if I share this code with you right now, if I don't include this random.seed, you might get different results than what I'm showing. But if you just use this random.seed, then all the randomness will be initialized in a very similar manner. So I'll run this and you will see that the green tick will appear here. Great. And now we'll define the model architecture. So now we have looked at the training data, the testing and validation, and we have standardized all the data set. We'll now be defining the neural network architecture. So here you can see that I've used keras.model.sequential, and then we'll sequentially stack different layers in front of each other. So we'll be having two dense layers. The first dense layer has 30 units. It has the ReLU activation function. The second dense layer has 10 units and it also has the ReLU activation function. In the first layer, we have to specify the input shape, but in the second layer, we don't have to do that because the input of the second layer will just be the output of the first layer. And then finally, the output layer will just be a layer which has one unit. Since it's a regression problem, we just need one value. Based on all of these 8 features, finally we need one value, which is the price of the house. And we could have used an activation function here, but it's not needed because it's a simple regression problem. You can try with an activation function here, like ReLU, for example. Since price will always be positive, you can use ReLU to make sure that the output always is greater than 0, since the price of a house cannot be less than 0. So this is the model architecture, and you can play around with this. Try different activation functions, try different units in the neural network, etc. Then what we'll be doing is that we'll be specifying the loss function and the optimizer, and that is done through this command called model.compile. Now, since this is a regression problem, the most optimum loss function to use is the mean squared error loss. And the optimizer, we have used the stochastic gradient descent. You can even use the Adam optimizer and you can see if it gives better results. But I've used the stochastic gradient descent or SGD, and I'm specifying a learning rate of 10 raised to minus 3. And then the last command here is the model.fit. This will actually run the training of the neural network. And here also we have to specify a few things, like we have to specify the number of epochs. So I'm running for 20 epochs, and I am specifying the validation data, so that along with the training loss, we'll also be reporting the validation loss. So when I run the epochs, I have the training loss, and I will also print out the validation loss. Remember that the training loss does not mean anything unless the validation loss is really minimized to a lower value. Ultimately, what's important to us is that the neural network should do a great performance on data which it has not seen before, which is the test loss and the validation loss. So remember that there is a lot of scope for hyperparameter tuning or optimization here, which I'm not covering in this video. You can change the number of units, the activation function, the optimizer learning rate, the optimizer itself. Then you can change the number of epochs. You can add a dropout layer. You can add a batch normalization layer. And it's very easy to add different layers. You can just use the keras.layers.batch norm or keras.layers.dropout. So dropout and batch normalization is important if you want to add regularization. We have not even added a regularization term in the loss here. You can add it if you want the model to have a good generalization performance and avoid overfitting. So let me run this right now. And as you can see, I have already run the model before making this video, so that you can clearly see the results from different epochs. So I've run 20 epochs, and remember, one epoch is going through the entire data set once. And in each epoch, I'm printing out the training loss and the validation loss. So let's move sequentially down and see what the final loss is. You can see that the loss, both the training and validation loss, is steadily decreasing. Well, not quite the validation loss, because it seems that the validation loss is actually increasing towards the end. Um, so let's look at the final values. The final value of the training loss which we get is 0.4056, and the final value of the validation loss is 0.052. Now, how to know whether this is a good value or not? The best way to understand is to plot the training and the validation loss. So here you can see that after running the training loop, I've plotted the training and the validation loss together, so that we can understand whether the hyperparameters which we have chosen are correct or not. This process is usually done along with trying different hyperparameters. So we can see the validation loss in the orange, and we can see that the validation loss has actually started to increase after, I would say, after about 10 epochs. And the final validation loss is much higher than the final training loss. This is actually a great sign of overfitting. This is a sign that our model is not generalizing well. Ideally, the training loss and the validation loss should be very close to each other if your model is having a good generalization performance. So, what I should be doing right now is that I should be taking steps to prevent overfitting. And the way to do that is many things. You can add regularization, you can add dropout layers, or you can just make the model a bit simpler. So right now, what I'm going to do is that I'm just going to remove one layer. I'm going to remove this second layer, which has 10 units and one activation, and I'm just going to have one layer as the output layer, which has one output. That's it. So you see, I'm making the model simpler so that the generalization is better. I want you to remember the final validation loss which you obtained here. It's 0.52, and I also want you to remember the final training loss, zero point 0.4. Now let's see the effect of making the model a bit simpler. Okay, so let me run this parts of the code again. So I'm running this where the X data set is imported. This part is run, and then let me run this part again where we standardize the data, and this part again where we set the random seed, and finally I'll run this model training. Okay, so the model training is running, and the loss and the validation loss have started out from low values. But remember that last time we stagnated at a validation loss of zero point 0.5 and a training loss, I think, of around zero point 0.4. So the first thing already which we can see from here is that the validation loss is closer to the final training loss. This is a great sign because it is a sign that we have reduced overfitting. So I want you to take a look at what we have done again. We removed one layer completely and we just had smaller number of layers. We made the neural network simpler and it reduced the validation loss by zero point 0.1. In the last case where we had a larger neural network architecture, we actually had a validation loss of zero point 0.4, zero point 0.5, but now we have a validation loss of zero point 0.4. So let me plot the losses here again. So I'm plotting the training and the validation loss now, and here you can see the training and validation loss has been plotted, and now the validation loss does not seem to show an increase after 10 epochs. If you look at the orange curve, which is that of the validation loss, in the earlier case where we had a larger neural network, the orange curve was showing an increase after certain number of epochs, which is a sign of overfitting. But now the validation loss and the training loss are showing a steady decrease, which is great, which means that we have avoided overfitting. So these are some steps which you need to do yourself when you are optimizing the hyperparameters. Now, this can be improved even further if I try out various other activation functions, units, different optimizers, different learning rates, etc. I believe this loss can be brought down to around zero point 0.2. So I believe the training loss can be brought down to 0.25 and similarly for the validation loss. So I invite you all to experiment with this and comment in the video section how your iterations proceeded, what's the minimum loss which you obtained, etc. We'll be replying to all those comments to help you navigate your way through this hyperparameter optimization. Finally, after fixing on a good set of hyperparameters and seeing that the validation loss and the training loss is similar, we can actually evaluate the performance on the testing. And ideally, if the generalization is actually good, the testing loss should be similar to the training and validation loss. And in this case, it's similar. All of them are close to zero point 0.4. So if you scroll up, you will see that the final training loss is zero point 0.2, final validation loss is zero point 0.4. And right now, we just evaluated the final testing loss. So let me show you what that is. And we saw that the final testing loss is actually 0.41. So all these three losses are close together. Although these losses can be reduced much further, it's at least a good sign that we are not overfitting and the model is generalizing well. Finally, we can actually take some samples and make our prediction on the test data set and actually compare what the housing price ground truth data is. So from the testing data, I'm going to take the first three samples and I'm going to predict using my model. I'm going to predict the housing prices for these three sample houses, and I'm going to compare it with the actual housing prices, and I'm going to show you the comparisons for my neural network prediction and the actual price. So here we can see for three samples, I have shown you the predicted value and I have shown you the actual value. So you can see that for all these samples, the predicted and the actual are slightly close to each other. They can be made better. So for example, in sample 2, the predicted is a bit higher than the actual, whereas for sample 3, it's a bit closer. And this is because the loss function can be decreased even further. When I tested out in my trials, I have seen that if you use a learning rate of 0.005 and if you increase the epochs to 60, then you will yourself see that the loss decreases to around 0.25 or zero point 0.3. and that will make the testing predictions much better than the values which have been obtained currently. Remember that training does not matter too much unless you have a very good testing performance of your neural network. So don't just copy this code and run whatever I've shown you right now. Play around with hyperparameters and play around with the loss functions, the training loss, validation loss, testing loss. All of this becomes very important. During this lecture, I used many terminologies like regularization, dropout, and batch normalization, and ADAM optimizer. If you don't know about these terminologies, I would highly recommend you to go through our neural networks from scratch series where we have explained all of this. That's why it's very important to go through the theory, because unless you go to the through the theory, you will not understand what to change here to make this better. So since I know about the theory, I know that we probably need to play around with the learning rate a bit. We probably need to increase the number of epochs. We can change the activation function to tanh or sigmoid. So such things will automatically start coming to you if you understand the theory. But I wanted to show you this practical implementation so that it will also help you for your job preparation and you can add it to your resume. This is the California Housing Dataset project which we have implemented right now. And in the previous lecture, we have actually looked at another project which is the fashion data sorting project. So if you have not seen that video, I would highly encourage you to go through that, because that is an example of classification. And in that project, we saw how we can actually train a neural network to classify between different types of clothing. Today, the example which we saw is an example of regression, where we are just predicting one final value. So in the previous case, we use softmax in the last layer activation function. In this case, we don't need to do that because we are just predicting one value and it's not a classification problem. So as you can see over here, in the last layer, we are not using any activation function. Over here, the layer which I'm highlighting right now, we are not using any activation function here because this is a regression problem. So I'll make one more lecture in the neural networks from scratch series, which is a recap of all what we have learned in this series. I hope this lecture was useful to you, and I hope you will continue to implement many more such projects using this video as a reference. Thank you so much, everyone, and I look forward to seeing you in the next video.